The Eutectic Welding Institute at Flushing, New York, teaches Eutectic's process of low-heat input welding. Many thousands of students from all over the world, technicians and ship and service the makers of Eutectic low-temperature welding alloys in the United States and Canada. These special process alloys are shipped from Flushing to users in practically every country in the world. This record explains the theory behind the process of low-heat input welding and how it differs from conventional metal joining. The various metals will be discussed, the reasons given for weld failure, the ill effects of high heat, and how many of these failures can be avoided by the use of low-heat input welding. Please open your manual of instructions. This contains the illustrations we normally give on the blackboard and will enable you to follow the subjects discussed. Lesson 1 shows how Eutectic's process differs from conventional methods. Most metals undergo unfavorable changes when subjected to high heat. The higher the heat, the greater the expansion. On cooling, the metal may not return to its original shape. Brass contains copper and zinc. If it is heated beyond 1350 degrees Fahrenheit, the zinc will vaporize. Fusion welding had all these disadvantages, and a means was sought to join metals at a lower heat. The low-heat input process was conceived and begun in Switzerland 50 years ago, and continued and perfected by Eutectic in the United States during the last 15 years. The term welding has become associated in most people's minds as the very ultimate in strength, until the metallurgical meaning has been lost and welding has come to mean the highest possible strength. The word welding means heating two pieces of metal to their melting points and allowing them to flow together until they form one mass. It has nothing to do with strength. It merely refers to one method of joining metals which is not necessarily the best. Cast iron melts at approximately 2300 degrees Fahrenheit. This is the heat required for fusion welding. It can be joined at 1300 to 1600 degrees Fahrenheit if the low heat input method is used. During the joining operation, the cast iron at the surface of the joint is changed temporarily to steel. Carbon is removed. The special cast iron filler metal alloys readily to this surface, and the joint is completed hundreds of degrees below the melting point of the cast iron. How is this possible? By the diffusion of the atoms of the base metal into the filler metal, promoted by heat and a solvent. 1400 degrees of heat are required to melt a block of salt. This can be reduced to only 33 degrees of heat if a solvent is used. Water heated to 33 degrees Fahrenheit will dissolve salt. Over 1350 degrees of heat have been saved. This is illustrated on page 1. This is the principle of low-heat input joining through surface alloying. The base metal is not melted. It is dissolved by and surface alloys with the low melting point molten filler metal. Solid metals can be dissolved by molten metals just as salt is dissolved by water. Copper melts at 1981 degrees and silver at 1762 degrees Fahrenheit. Yet if a piece of copper foil is sandwiched between two sections of silver, it will alloy with the silver at 1450 degrees Fahrenheit. See Figure 2. The alloy is formed at the interface of the joint and is therefore called a surface alloy. The degree of alloying depends upon the affinity and diffusibility one metal has for another, the wetting properties, and the composition of the chemicals when a flux is used. Intensive research has been undertaken by Eutectic to develop a series of alloys with low melting points. High purity metals produced by the most modern refining and alloying techniques, have further enhanced the flow and wetting properties of these new brazing-type materials. Figure 3 shows how the melting point can be lowered by careful alloying. The process shows economical advantages as well as metallurgical ones. Consumption of gas, oxygen, and electricity is lower. The time involved is considerably less. The higher fluidity of the alloys permits larger assemblies to be completed rapidly. Long lap joints or large square butt joints take less time to complete. Less chamfering of joints is required. Less material is used. Machining is simplified, and finishing operations often eliminated because of the smooth, neat fillets obtained. Freedom from spatter reduces cleanup time. Highly skilled operators can be released for other work because of the simplicity of applications. Specifications indicate only the minimum requirements. Eutectic's alloys not only meet required specifications, but almost invariably exceed stated requirements. They fulfill an industrial need which could not be satisfied by conventional materials. There are over 150 alloys listed in Eutectic's range. The average shop needs about 20 for everyday use in production, maintenance, and construction. The others are for special applications. Since the base metal is not fused and the input of heat is so greatly reduced, the process is called the low heat input process. The bonding temperature, figure 4, which is the heat to which the base metal must be raised for the molten filler metal to surface alloy with it, depends upon the base metal, the filler metal, and upon the type of joint. The design of the joint has a distinct bearing upon the amount of heat necessary to effect a bond. You will see the various types of joints illustrated on pages 5, 6, and 7. Each requires a slightly different treatment to obtain maximum results. Less heat is required for open chamfer joints, fillets, and overlays. More heat is needed when the filler metal has to flow by capillary attraction through square butt or lap joints. The flux plays a most important part in the low heat input process. A special alloy is needed for each metal and a special flux for each alloy. The flux has many specific duties to perform. Dissolve surface oxides, prevent formation of oxides during heating on the base metal and filler metal, and reduce surface tension. Basically, there are two different techniques used when applying these alloys: bead forming and thin flowing. Bead forming uses the lowest heat and is used to fill a V or to build up a section. Thin flowing alloys are for close-fitting joints. A slightly higher heat is needed to thin flow the alloy. The principles of low heat input have been equally successful when applied to metallic arc welding. The bond is obtained with lower current values. The result is a reduction of heat into the parent metal. The amperage is lower, the voltage less, and therefore the watt input is reduced. Please turn to page 8. These are the three types of flame used with an oxyacetylene torch. Excess acetylene has the lowest heat, and an oxidizing flame the highest heat. Study these drawings so that you may fully understand the relationship between the type of torch flame and the angle at which it is used. The corresponding flux is always used with each alloy. Furnace and induction heating are economical methods for production operations. Thin-flowing alloys may be pre-placed in the form of a ring, brushed with the correct eutector flux, and the joint completed in a furnace without further handling. Figure 23 illustrates this method. The newly developed Eutec tin weld and sill weld are combinations of alloy in powder form, mixed with specially compounded fluxes. They can be painted onto the joint area and will replace rings or shim. You will see illustrations of AC and DC machines. All you Tektrodes are marked AC, AC-DC, or DC. This specifies the type of current which should be used. You Tektrodes can be used with most types of welding machines manufactured today.